For today's video, we will be talking about E1 reaction. E1 reaction is an elimination reaction that is very similar to an SN1 reaction. And so if we have an example that looks like this, bromine, and let's say the reactant of this reagent is water and heat. So we know heat is high temperature, and elimination happens at high temperature. That is why we have heat. For E1 reaction, it doesn't matter what kind of nucleophile it's been using, bad or good. You can do both, similar to an SN1 reaction. But it needs a good leaving group, such as this. E1 reactions can happen at a primary carbon, secondary carbon, or tertiary carbon. The tertiary carbon is the fastest reaction for an E1 reaction, and as an E1 E2 reaction, same thing. So when doing the mechanism for this, the first thing that leaves is the leaving group. The leaving group leaves, and so we would get a product of this. A carbocation forms. We look around to see if there is anything else that can move, a hydride shift or a methyl shift, so that it can become more stable. In this case, everything's equal, everything's secondary. So now we would look at the alpha carbon and look at the size to see the beta carbons. And we have two in this case, one carbon away. We see that there's 3 hydrogens on the left, but we're going to use one of them. And there's 2 hydrogens on the right, but we're going to use one of them. In this case, it does not need to be anti-coplanar like E2 reaction. So no need to look for its anti-coplanar. You can just do the reaction for this. The second thing that happens is that the reagent comes in, the water. Water comes in with its lone pairs, grabs the hydrogen, and forms the double bond where the carbocation is at, by the carbocation. And so this will give us a product that would look like this. And this is one product. Let's redraw this structure again over here. So if we have this, we use the left side already. Now let's do the right side. So water comes in again to get our second product because we have 2 beta hydrogens. From here, the lone pair of oxygens goes to the beta hydrogen. This beta hydrogen gives off electrons to go to the carbocation. And so from here, we get another product that would look like this. So we have these two. The same will apply for E2 reaction, which was major and minor. And so the major product is always the more substituted product, which would be this major, and the top one is the less substituted because this is called the minor. And also the naming is still the same thing, Hoffman and Zaitsev, but in E1 reaction, Zaitsev is always the major product. So Hoffman is the minor, always for E1, and major is always the Zaitsev product for a major product. So Zaitsev meaning more substituted, Hoffman means less substituted. So let's do another problem. In this case, let's say this is actually reacting with water and also heat. So if you ask yourself, why is this an elimination reaction? An E1 reaction, we say that there's heat. High temperature only happens at elimination reaction. But also, as the reagent, we see there's water. Water is not a good base. It's not really a good nucleophile. In this case, E1 can happen at a good or bad nucleophile. And this is why this is an E1 reaction. But also, there is a good leaving group. So this fulfills this as an E1 reaction. So E1. Now the first things first, the leaving group leaves. And so we get a product that will look like this. Carbocation forms. We look at the structure and see if there's anything that can move to make it more stable. In this case, there is a methyl shift can happen here. Goes and attacks the carbocation, and we'll get a product that will look like this. So now the carbocation moves to here. So now we're looking at this carbon. We look at the beta carbons, and we see there's one hydrogen here and one hydrogen here. In an E1 reaction, the reagent goes and grabs the beta hydrogen and forms a double bond. So in this case, water will come in. The lone pair of oxygen will go and grab that hydrogen. This hydrogen gives off an electron to form a double bond here towards the positive charge. It doesn't go here, nor does it go here, but it will go on that carbon, that double bond on that carbon by the positive charge. When this happens, we get a reaction that will look like this. And that is it. Because if you do on the other side, if the water would come on the other side and grab that beta hydrogen, it's actually the same thing. Go and grab it, and then this moves over here. This is actually the same thing, because if you look at the molecule, it is achiral. If you bring it down, the left and the right are similar, are the same. That means it is the same thing if you do it on the left. So in this case, there's only one product for this. And also let's add the byproducts, which is H3O+. So there's an answer for this problem. Let's do another problem. We have the structure. Bromine right here, and this is reacting with, let's say, water. Okay. We see that there's elimination. Elimination because there's heat. Heat is high temperature. We see that there's water, not a good base. E1 reaction happens at a poor base. Also, we have a good leaving group. E1 can happen on this reaction. So the first things first, the leaving group leaves, and so we get a reaction that will look like this. Positive charge here, carbocations formed. We ask ourselves if there's anything else that we can make this to make it more stable. We see that there's a hydrogen here. So a hydride shift can happen, goes and attacks the carbocation. This will form a bond that will look like this. Okay. But now there's a positive charge here. When this happens, we look at the beta carbons. We have 1, 2, and 3 beta carbons here. We look at the hydrogens. 1, 2, and 3 beta hydrogens. There's more, but I'm only going to pull one of them off. So in this case, if we had a double bond here formed here, and also had a double bond formed here, it's going to be the same thing if we put it on the bottom, or if we put it on the top, because it's going to look like this. If we put the double bond here, or if we put it here. These two are the same thing, and so in this case, we're going to pick one of them. In this case, I'll pick the bottom portion of it. So no need to do both. So now water would come. Goes and grabs the beta hydrogen. This beta hydrogen, its bond, will go and form a double bond here, which will give us this product right here. This plus the second product. Our second product. Water will come again and now attack. You should draw it separately, but I'm going to just draw on the same structure. Comes and grabs this beta hydrogen. This beta hydrogen forms a double bond where the positive charge is at, so over here towards the positive charge, and will give us the reaction over here like this. And so we know this is the major because it is more substituted. also is the Zaitsev, right? Zaitsev, and this is the minor because it's less substituted, so it's called a Hoffman. And so these are two products for this problem. Let's do another example here. If we have this structure, and this we have chlorine, and this is reacting with, let's say, methanol. And we have heat underneath. So we know this is heat. Heat happens at high temperature. Elimination happens. Here we see that this is a polar product solvent. So that means I said E1 is very similar to an SN1 reaction. They use the same, they use the polar product reagent. And so this is a polar product solvent, and this is an E1 reaction. We have a good leaving group as well. So E1 reaction happens, the leaving group leaves. And so we would have a structure that would look like this. A carbocation happens here. This time we see that there is a methyl. So a methyl shift happens and attacks the carbocation to make it more stable. And so we get a result of this. Okay, now the carbocation is over here. In this case, again, we see that there is 3 beta carbons. 3 beta carbons. But again, this and this are the same thing, so just pick one of them. Let's pick the top one. And so we have another beta hydrogen here. And so now we have to pull it off with the methanol. So the methanol comes in. Let's do the top one. OH goes and grabs that hydrogen. This hydrogen forms a double bond where the carbocation is at. And so we'll give a reaction of this. So this is our first product. Now I'm going to redraw the reaction here with positive charge, the carbocation. So this carbocation here. And then we have the hydrogen here, the beta hydrogen. So now ethanol will come again. It goes and grabs that beta hydrogen. This beta hydrogen gives off some electrons to form a double bond here. So this will give us a final product of, oh, I forgot about that. Final product that will look like this. These two are a final product for this structure. The one on the right, it is the major product. It is more substituted, meaning more substituted because if you look at these 2 carbons, it is attached to 1, 2, and 3 carbons. You look at this carbon, these 2 carbons, it is only attached to 1 and 2 carbons, so this is less substituted and this is more substituted. So the major is the more substituted carbon, and the minor, it is the less substituted carbon. So the Zaitsev would be the major and the Hoffman will be the minor. Let's do another example if we have this structure. And this is reacting with, let's say, concentrated H2SO4, H2SO4, and we have heat on the bottom. So we know this is an E1 reaction because we have heat. Heat only happens at elimination reaction. But also this time we see that there's concentrated H2SO4. This is because there's OH in the structure. OH is a bad leaving group, so OH is a bad leaving group, and this is why we need a catalyst to speed it up. That's why the concentrated H2SO4 is used in this. So you would only see concentrated H2SO4 with alcohol because alcohol is a bad leaving group. So instead of the leaving group leaves, we would actually have the structure of H2SO4 taking place. So H, we have oxygen, and then S, O, a double bond, oxygen again. All this oxygen has 2 lone pairs. And so the first things first for this now, the oxygen's lone pair of the OH goes and grabs the hydrogen. This hydrogen gives off the electrons to oxygen, and so we would have a structure looking like this. Oxygen now forms water, but has 1 lone pair. positive charge. Now it is able to leave, so the leaving group leaves. So this will give us a result of having a carbocation formed here. Look around to make it more stable, but it doesn't need to because this carbon over here is already tertiary, so no need to make it more stable. In this case, actually, we have to see the beta carbons. In this case, we have 3, and so we would have 3 products, but these two are the same thing. Same hydrogen, the hydrogen will be the same thing. So let's pull off one hydrogen here, one hydrogen here. So it's the same thing, really, technically, for these two. It would form the same thing, because if we move the double bond here, it'll be the same thing if we move the double bond here. If we move it here. Okay, so let's just pick one of them. So we're going to pick the bottom one. So we see the beta hydrogens here, and then on the right side, we have one right here. So 2 products for this case. Now we use our reagents. The H2SO4 will come back in play. So in this case, the H2SO4 will come back. Okay. It'll come and grab the hydrogen. This hydrogen will give off the electrons to form a double bond here. And so we would get a product of this. That's our first product. Let's redraw the same thing we had here. Positive charge here, and this hydrogen over here. So now HSO4 comes again. Negative charge. One of the little pairs goes and grabs the hydrogen. This hydrogen gives off the electrons to form a bond here. And so we get a result of having it like this. And these are 2 products that we have for this. So for this, the more substituted is the major, which is the bottom portion. This is also called the Zaitsev. And right here, this is our, this is our minor on the bottom part. This is our Hoffman, because it's less substituted. And this is our major, which is the Zaitsev. So these are 2 products we would have. So now what if we have this structure? So when we see OH, our reagents would be actually concentrated H2SO4. And would be heat. So again, we use a concentrated H2SO4 because OH is a bad leaving group. It's a catalyst to speed up the reaction. We see heat, and this is used for high temperatures, used for elimination. So this is an E1 reaction. So now instead of the leaving group leaving first, we would have the H2SO4 coming. Right here, and all the oxygen have 2 lone pairs. And so the oxygen from the OH from the problem, it goes and grabs that hydrogen. This hydrogen gives off the electrons to this oxygen, and so we would have a reaction of, again, forming the water. This time, this water would have a positive charge, and now it is capable of leaving. So leaving group leaves. We would get a structure that will look like this. Forming a carbocation over here. Now we ask ourselves if there's anything else we could change this to make it more stable. We see that there's a hydrogen here on this carbon, so a hydride shift comes to that positive charge to make it more stable. And so this will give us a reaction that will look like this. And now the carbon cation goes right here. From here we see that there's 3 beta carbons here, here, and here. Well, here and here. We're going to pull off 1 hydrogen here, 1 beta hydrogen. So that's a beta hydrogen here, there's a beta hydrogen here, and there's a beta hydrogen here. I know there's 3 here, but we're going to use 1 of them. There's 2 here, but we're going to use 1 of them, and there's only 1 here. So there's 3 beta hydrogen in this case, 3 separate beta hydrogens. Like the last problem, we had 2 of them being the same, so we used 1 of them. In this case, they're all different. We have a primary, tertiary, and then we have a secondary right here. In this case, it would be 3 products for having 3 beta hydrogens. So now, let's start on the bottom. HSO4 comes in. H2SO4, right, negative charge. Grabs that beta hydrogen, and it forms a double bond here. Okay, they will give us a product of this. Let's put it up here. A double bond like this. First product. Second product comes. Let's have the H2SO4 come over here. Negative charge comes and grabs this hydrogen. This hydrogen forms a double bond where the positive charge is at. So this will make a product of this. And this is our second product. Finally, for our last product, let's put H over here. Grabs this hydrogen. This hydrogen forms the double bond here, where the positive charge is at. We go towards the positive charge. This will give us a reaction that will look like this. So 3 separate products from this case.